Last time we talked about the disk method, where we took the volume when we rotate the square root function around the x-axis. Well, now we are going to expand the disk method to find some more versatile volumes. So when I say a versatile volume, what I'm talking about is something like a napkin ring. So say I have this napkin ring, and maybe it bulges out a little bit. So it bulges out a little bit here, and then here's the inside of the napkin ring, and then here's this kind of goes back, There's our napkin ring, and it's got a certain thickness to it. So it bulges out and it's got a thickness. So how would we deal with this? So what we do to find the volume of this napkin ring type thing is we use a more nuanced version of the disk method, where instead of just one function being rotated about the axis, we take the area of a region and we rotate that about an axis. So now this becomes something hollow almost. So say I have a function that looks like this, and I have a function that looks like this, and I have this region that is then created. And what I want to do is now I want to rotate this around the x-axis, and that is going to become something that looks roughly like this. And we are going to get a napkin ring type thing. We're going to get like a washer almost. And it's going to give us like a tube, but a weird shaped tube. So that's how we can use the disk method to find some more complex shapes. So now let's do an example with that. So I'd like to find the volume obtained by rotating the region between x squared and x. So as always, what I like to do is draw this out. So here's our line, f of x is equal to x. But now we are left with a problem. Now we need to find our bounds of integration. We need to find our intersection points that make up our region that we will rotate around. So to do that, what I do is I set x squared equal to x. Those are our two functions. And if I move x to the other side, that gives us x times x minus 1 is equal to 0, giving us solutions of 0, 0, and 1, 1. So that means that we are going to have a solution here, and we are going to have a solution here. And our parabola is going to look something like that on this side. So we're going to be taking this region, and we are going to be rotating that around the x-axis. And that is going to give us kind of a cone, an empty cone. It's going to be a pretty cool looking shape once it's finished. So why don't we get started with that by setting up our integral. So we know that the volume is going to be equal to the integral between 0 and 1, as those are now our bound points. So we have 1 here and we have 0 here of our a of x dx. Now let's take a peek at the cross section to determine what our radius is. So here's a cross section. Here we have the circle created by f of x is equal to x. Here we have our circle created by f of x is equal to x squared. So our radius, so the radius is going to be equal to our radius of our x minus the radius of our x squared. Because if this is our x squared, this is our x, then our radius is going to be equal to this here. Okay, so it's going to be this little thing in here, right? All right, so let's set this up. So we're going to get a of x is equal to pi r squared. That should be pretty simple. And that will be equal to our radius of the x, or our area of the x. So we're going to get pi x squared minus pi x squared squared. That's going to give us pi times x squared minus x to the fourth. Now, this is our a of x. Now we are prepared to set this into our integral. So this is going to give us the volume being equal to the integral between 0 and 1 of pi times x squared minus x to the fourth dx. Now, as always, we can pull out that pi, and that gives us the integral between 0 and 1 of x squared minus x to the fourth dx all times pi. Now, all that's left to do is some simple monomial integration and applying the fundamental theorem of calculus. So we get pi times 1/3 x cubed minus 1/5 x to the fifth. Evaluated between 0 and 1, of course the 0 term goes away. That gives us pi times 1/3 minus 1/5. And if we do out that arithmetic, that gives us a final sum of 2 pi over 15. And that is our final answer for this example. In the next video, we're going to be looking to the second method of finding the volume, the volumes of the solids of revolution. That's going to be the cylindrical shell method. So we will look at that later. Thank you very much for watching, and we will see you in the next one.